Okay, thanks. And you're going to reset the clock for me too, or is it the clock is running already? Okay. Okay, let me again recap everything I did in the last 20 minutes, which is basically that if we have two measurements from the experiment and the control, the question, and let me make them bigger, the question we would like to ask is the experimental value different, is the experimental value different than the control? But we can't ask that question because mathematically we don't know how to do that. So we're stuck. We can't ask this question. The only question we can ask is the difference between the experiment and control due to chance? And that's the question we can ask. Okay? This we can't ask because it's not clear what this word different means. That's the reason why we can't ask this first question. What does it mean to be different? So that has no meaning. But we can say if they're both from a distribution, is the difference due to chance in those means of the two distributions? That's the question we could ask. And that's why we have to go through this whole contorted nonsense with the H-naughts and proving the H-naughts true or false and everything like that. Because this is the only question we know how to ask. Now, let's see different ways that we can compute the probability values to answer this question. The case we've been dealing with is where we know m naught. We know the true mean. How do we know the true mean? It's someplace in my notes that I was reviewing this morning before coming in here. One place it says, we know the true mean mystically. So that's apparently we know the true mean somehow from one form or another. Like we're comparing data to some probability function we can calculate directly. So in this case, the z value is the experimental value, experimental mean, mx, minus the mean that we calculate divided by the standard deviation of the mean from the experiment. And as I said before, the standard deviation of the mean from the experiment is equal to the standard error of the mean is equal to the standard deviation of the experiment divided by the square root of n. So I can rewrite this z then as mx, I'll write m naught. So m naught is the mystical value that we know, mystically known. Should probably put it in a pyramid here. So if I replace this by that, I get sigma here over the square root of n. And I said this is what I use when I compare, well, let me not do that, say that. Okay. Now, it turns out we could use this formula to calculate p-values when we know the mean. So this is a specific case where the mean is known, the true mean is known. But this formula is based on the fact that n is very large. And n is not always very large. So the guy who I've mentioned a couple of times, W.S. Gossett, who worked for the Guinness, how do you spell Guinness?
2 N's, I believe.
1 S?
2 S's.
2 S's. Okay.
Is it 1 N, 2 S's? It might be 1 N.
Well,
I should know this.
You should know this. I guess having these is counter functional to remembering how to spell it. Is that how it works? What's sort of scary that people, it doesn't look right at all. In fact, I think it's 1 N. In my notes I have
there's 3 S's.
Okay. He wrote under, as I said, the name of student and developed something which is called a t-test. And basically what Gossett did was to show that this z statistic is not valid when n is less than infinity. And when n is less than infinity, we should use a different statistic, which is usually abbreviated as t, which is the experimental mean minus the known mean. So again, we're in the same situation where the mean is known, divided by the standard deviation over the square root of n minus 1. And the number of degrees of freedom, so this is one of these things with number of degrees of freedom, is equal to n minus 1. Now, the reason why I've gone through the derivation before, I mean, what I'm doing here is actually never done in textbooks. I'm trying to give you motivation, not so much to derive the test mathematically, but give you a sense of the motivation of where all these statistics come from. And that's what I'm trying to do here. And I've really emphasized the z statistic is the difference between the experimental and a known value, and it has this form. And now we can see how this form is related to a real statistical test, a t statistic. You can see that we've replaced the standard deviation of the population, which is presumed known, by the standard deviation of the sample, which we may not, because we don't know this sigma, so we used s. And as I derived once before, when we use s, it's better to replace sigma by n minus 1. So you can see now where the n minus 1 comes from, that it's because we're using the sample rather than the population. And you can see where the whole form of t comes from, that is really based on the z form that I've just been showing you. So what I'm trying to give you a feel in these statistical tests is where the statistics comes from, rather than going through the formal derivation, but give you sort of these hand-waving arguments so you get a feeling of why we're using these combinations of symbols. Okay. And the way we do this is you can compute these values of t from the data, and then in order to get the p-values, p will depend on t and the number of degrees of freedom, which is a number of data points minus 1. And we can either look this up in a table, in the back of a book or a special book that we buy. We can compute these values from Abramowitz and Stegun's book, which I mentioned a number of times, called Handbook of Mathematical Function. And we can also, many statistics programs produce these t-values also. And again, we have the option, just as we had before, of doing a one-tailed or a two-tailed test. Depending on whether we're asking, a one-tailed test means, is the t-value greater or less than a value that we wanted? And a two t-tailed test is the t greater or less than the value that we were expecting. So again, we have the one or two t-tailed business. Okay. Let's say that the known mean, like we had before, was 6.0. Okay? And in the data, we have 10 values. And we calculate the mean of the data. Let's say the mean of the data turned out to be 6.5. So we could ask two questions. The first question we could ask, you know, whatever mean we got, was that mean going to be greater than 6? Or we could, because we got greater than 6.5. That is, we got 6.5. What's the probability that we would have gotten 6.5 or bigger? So in order to do that, we would look out here. If this is 6 and this is 6.5, and this distribution is no longer a Gaussian distribution, but a different distribution which is based on the t statistic. So it's not a Gaussian anymore. We have to look up in a different set of tables what the area is here. And this area over here will give us the probability that it was 6.5 or greater. Okay? You understand the one-tailed test. The two-tailed test asks a question. We got 6.5, but the question we're really asking, is it not 6? So this time we got 6.5, but maybe if we also would have gotten 5.5, we would also say it's not 6. So the two-tailed test, we have to add the probabilities at both ends. The probabilities of getting 6.5 or greater or less than 5.5. So in this question, we're really, you know, because if in this case we just happen to get 6.5, but if we got 5.5, we would equally say it's not 6. So the two-tailed is saying it's not what we think it is, meaning it's either greater than that offset or greater than the equivalent negative offset. And if we would have gotten 5.5 on the experiment, we would ask whether it's greater than less than 5.5 or greater than 6.5. Does that? Okay. But in this case, we look up in these tables, or I have a computer program, again, unfortunately, in BASIC that doesn't run anymore, that produces the t-values. Okay. So the first case, what we've looked at, or where, in the first case, where we have a known mystically, a known value of the correct mean and standard deviation. Now let's look at the more typical experimental situation, where what we have is we're wanting to compare two experimental values. So for example, I'm measuring reaction times of people. And one group is the control, and their reaction times are 5.3 plus and minus 1.2. And the second group is this Guinness group, and their reaction times are 7.6 plus and minus 2.1. And since this is me, of course, I've given you plus and minus the standard errors of the mean. So the question is now, is the difference between these experimental and control numbers due to chance? Okay? Does everyone understand how this is different from the first case? In the first case, we knew what the mean was, what the true value was. We're asking, is it different from the true value? And now we don't know the true value of either of these. We're just asking if they're different from each other. Okay. And the first issue that comes up is we could have the same business between one and two-tailed. That is, we could ask whether the difference is significant, or was one larger, or was one smaller, or was both. So we have the same business between a one-tailed and a two-tailed tests. And what we want to do is to develop a statistic that's kind of like this statistic we used before. So in a certain sense, what is Z going to be? Z is going to be the mean of the control group minus the mean of the experimental group divided by the standard error that somehow represents the combined standard error when we subtract one from the other. Because we said when we do an operation on the data that the SEM increases. So we want to use somehow the combined SEM and the differences between the data. Or I can say this a different way. What we're really looking at here is a distribution function f, which is the difference between the experiment and control. And so we must find the value of the SEM that's really related to the SEM of f. Okay? So what we need to do in order to make this test meaningful, we know that mx is 7.6. We know mc is 5.3. We know that the SEM of the experimental group is 1.2, and the SEM of the control group is of 2.1, and the SEM of the control group is 1.2. So we have all this. What we want to compute is the SEM of f from the SEMs of x and of m and x. And the formula I showed you before, remember, was that the combined SEM is the square root of the derivative with respect to the two variables, mc with respect to the standard deviation in mc squared, SEM and mc squared, plus with respect to mx squared, SEM of mx squared. Well, if the function f is the mean minus the other mean, then the partial derivatives with respect to each one are 1. Okay? So this means that the SEM is equal to the square root of the SEM of the mean of the control group squared plus the SEM of the mean of the experimental group squared. Now, what are these two things equal to? We said the SEM is the control group squared variance divided by the number of people in the control group. So that's this thing squared. So let me square it. Plus this thing is the experimental group standard deviation squared of the population divided by that squared. So this SEM of the combined group is like this for the individual groups. Okay? So now the t statistic is going to look something like, or the z statistic will be the difference between the means of the experimental and control group divided by sigma control group squared over, there's no squares here, sorry about that, plus sigma experimental squared n squared. Okay. Okay, so this is now the procedure. If we have an experimental and control group, we can now determine the value of z and see if the difference between the experimental and control values are statistically significant or not. Now again, this is assuming that everything is Gaussian. That is, that the numbers nx and nc are very large. Again, in terms of the t statistic, now we can rewrite this as the difference between the mean, the experiment and control, divided by sigma squared over nx squared plus sigma squared over nc. Now, this is now based on the assumption that both the experimental and control have the same population variance. Well, what I'm trying to do, again, is to try to give you a feel for where these statistics come from. And we've seen now that the original z was the difference of the experiment minus the control over the standard error. If we know absolutely, the true values, we don't have a standard error of the theory. But when we have two different values, then we have the standard error combined of the two values, which is this. So this is where this term comes from. And now in the t statistic, we start off in deriving the t statistic with a very similar form to that. The question now in terms of the t statistic is, what is this sigma? That is, what's the standard deviation if we have two different things? Well, if we have two things that we're adding together, we've seen before the usual way things add is like this, is the sums of the squares, the square root of the sums of the squares. What we want to do here is, since we're combining the two different data sets, the experimental and control, if there were more values in the experiment, we'd want to weight that more, count that more. If there were more in the control, we'd want to count that more. So really what we want is a weighting of the sigmas by some function. By some weighting function. And what is this weighting function going to be? The weighting function should be something like the number of values. So if we have more values in the control group, then we're determining sigma better from the control group than from the experimental group. So one way to write this then is to say sigma is going to be something like nx times sigma x squared plus ny sigma y squared divided by nx plus nc, nc, square root. Now here's where it says another mystical reason. The mystical reason here is that instead of using nx and nc, we actually use nx minus 1 and nc minus 1. So it means that the standard deviation we actually use in that formula is nx minus 1 times sigma x squared plus nc minus 1 sigma c squared divided by nx plus ny minus 2 square root. Okay? And this is also going to imply that the number of degrees of freedom will be equal to nx plus ny minus 2. Okay, and now where we're going to put this sigma that we got is back into the formula that we've been deriving, where I had sigma squared over nx and sigma squared over ny. So I'm now going to put that sigma into this formula. And where is it? I haven't actually done it, but that's where that sigma is. So this sigma is the sigma in this formula, and it represents in some ways a combined standard deviations from the two different groups. And that's the full way that the t-test is done. So in order to do a t-test, what we do is we have data. What we need from the data from the two groups is we have from the experiment, from the control group, its mean, its standard deviation, what if I've sorry, I've jumped ahead of myself a little bit. So let's get back to where we were. I'm sorry. We have sigma here, but what we actually have from the experimental data is S, which is the standard deviation. This is from the population. So the one additional test that we have to do here is we know that sigma S from the, if you remember what we did last time, was this with the n minus 1s here, in order to get the population variance from the actual data, whereas the derivation of the standard deviation from the data is this divided by n. So what we really need to do is to know that n minus 1 times sx squared equals nx times sx squared, and then we can rewrite sigma. We can rewrite this off the top of the screen in terms of what we actually get from the data, which is nx times sx squared plus nc sc squared divided by nx plus nc minus 2. So this changes some of the numbers up here. It kills off the n minus 1s. And then the number of degrees of freedom is still nx plus nc minus 2. Because where I left things up here was that these sigmas come from the population, which we don't evaluate directly from the data. So this is the formula that we use to directly evaluate things from the data. So I've done this in sort of a tortuous way. It involves a number of steps, but they're all straightforward, actually. Again, what I'm trying to do is to give you a feel for where this formula comes from. To get back to where I was, and the formula is correctly in Spiegel's book. So what we do is we have experiment, and from the experiment we get the mean of the experiment, the standard deviation in the experiment, the number of values in the experiment, and from the control we know the mean of the control data, the standard deviation of the control data, the number of values in the control data, and from all of this stuff then we can get the t-value and the number of degrees of freedom. And from those, we can then look up what the probability p-value is. In the limit, where the number of experimental and controlled data goes to infinity, this becomes a Gaussian. So if you look at the end of one of these tables, at the very end, there are numbers where it says infinity, and that corresponds to the case where it's Gaussian. Now I have another case which I won't go through the derivation, because apparently it's not such a bad spelling day, but it's a bad derivation day. An interesting case, an interesting T case, is the case where we have the same amount of data in the experimental and control groups. And in this case, then, the T statistic, if you can show by going through the calculation, turns out to be the difference just divided by S over the square root of that number, the standard deviation. Again, this is kind of like the estimate of the standard error of the mean. So this is the difference between the mean of the experiment and control divided by the standard error of the mean. Again, you can see that these statistical tests are based what I would do when I would present experimental data. They're really based on the standard error of the mean. And that's why we get sigma divided by the square root of n in all these tests. Now, there's another issue that comes up. So far we've had one and two-tailed tests. Another issue that comes up has to do with pairing and what's called a paired test. Which has nothing to do with fruits. They gave me a nice little basket of fruit in the hotel. I like the orange and it's like a tangerine. The pear didn't look so good. I didn't eat the pear. Then there was another fruit which I couldn't figure out. It might have been a kiwi.
Is this in Israel?
In Israel. I was going to walk in this morning and say that I just flew back from Israel last night, and boy, my arm's tired. But luckily, I have too much class to do this. Maybe. So here we are back on the paired test. I can still picture it was like green with this brown rod on the side of it. And there was a small pair, too. What does a paired test mean? Very often in doing an experiment, we have the same subject received both the experimental and control treatments. So this is a within group or a between group design? Say it again? Within group, right. So if we have three people in the experiment, Fred, Mary, and Oscar. And we test their reactions when they have no alcohol and enough Guinnesses to do 3 N's. And we're looking at their reaction time. So let's say the reaction times were actually I have them here, 1.1, 1.3, 1.1, and with the Guinness, 2.1, 2.3, 2.4. So everyone is slower when they're wasted. Now, one way we could do this and analyze this data is we could do all of these data together and get some statistic, and do all these data together and get some statistic. So this is control, and and then compare them. But we have more information than that. We know that Fred, whether he's drinking the alcohol or not, is still Fred. And Mary is still Mary, and Oscar is still Oscar. So some of the variations between each of these is due to the fact they're different people, but there's less variation this way than this way. So in a certain sense, we can get a stronger statistical sense of what's going on, not by lumping everyone together, but realizing that we have the same person doing two different things. And so what we can look at is the difference between each person. The difference between Fred and Fred is 1.0, and between Mary and Mary is 1.0, and between Oscar and Oscar is 1.3. So if we compare the differences by person, then we may get more statistical inference. We may get a stronger influence because we have additional information than we had as if we lumped everyone together. And this is called a paired or pairwise comparison. And you should be able to see intuitively why this is going to be a stronger test. Because some of the variation is between Fred and Mary, but we're not interested in the variation between Fred and Mary. We're interested whether when Fred is drunk and Mary is drunk, they're really zapped and their reaction times are longer. So by doing this paired comparison, by using the differences, we can get a much stronger statistical test. Now let's look at why this works in a little bit more detail. This is a very useful thing to do if we have the same subjects. And I want to give you a sense of quantitatively what this amounts to. First of all, the t-statistic now will be the mean of these differences divided by the standard deviation of the differences divided by n minus 1. So this is the t for paired, where this is the mean of the differences. So we're analyzing the differences between the subjects in each of the two comparisons. Now let's see if I can show you why the paired is more powerful. Let's say if we look in terms of the variance or the standard deviations. If we look at an unpaired situation, what we're looking at is the combined combined standard deviation squared is the experimental one squared plus the control one squared. Right? This is what I've been telling you all along. Let's compute what happens in the paired situation. In the paired situation, we're looking at the standard deviation squared of the difference between the experimental and control. What does that look like? That's equal to the sum over I from I equals 1 to n of the xi of the difference between each experimental and control minus the difference in the experimental and control means squared divided by n. Okay, because this is what the pair is. This is the difference between the two, and if we're doing the variance of this, the standard deviation is the difference in between the two minus the means squared. So if I multiply this out, I can rewrite this a little bit is xi minus ci minus x bar minus c bar squared equals, you can write it as xi minus x bar squared minus ci minus c barred, sorry, squared up here, just rewrite it. Now I'm going to do the squares. So this is equal to xi minus x bar squared plus ci minus average c squared minus 2 times xi minus x average times ci minus c average. Now, if I put this term into the summation, again, this term is going to cancel, no, in this case, I don't want it to cancel. It's not going to cancel. If I rewrite this, I can, let me try to do this right since I spend the time doing it. What I have now is that the standard deviation squared of the differences is the sum of the first term, which is xi minus x bar squared over n, plus the second term, which is the summation of y of ci minus the average of c squared, minus this middle term. And I'm going to write the middle term as the sum of xi minus the mean x. I haven't canceled it out to 0 like I said I was, over this divided by n. This term is usually described, it's related to something which is called a covariance, and for the moment I'll just write it as XSY. This is kind of like the standard deviation combining the change in SXC, combining the data and the control, the experiment and control. It's kind of like a cross term. See, this is just terms from the experiment. You can see it as if I wrote xi minus x bar, and if I would have written c minus c bar, I would get this squared. So this is kind of like a cross term mixing the experiment and control. Or to say it in a different way, in the unpaired case, I have that the combined standard deviation squared is sx squared plus sy squared. And in this paired case, I have that the combined standard deviation squared is sx squared plus xy squared minus 2sxy, which is some correlation between the two. And this correlation, remember, is the fact that Fred is Fred, whether he's drunk or not. Now, let's say that the experiment and the control group are positively correlated, which is what I just said. Fred is still Fred. If there's a positive correlation between each experimental and control subject, then SXY will be greater than 0. And if this is greater than 0, it means the paired S squared is less than the unpaired S squared. Okay? Because since Fred is Fred, the paired S squared is less than the unpaired S squared. What does that mean? In all of these things in the t-statistic, the t-statistic depends on something like blah, 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 divided by S. So I've just shown you that in the unpaired, in the paired, S is lower. So if S is lower, it means the t-statistic is higher, which means we're going to get a lower p-value. So we're going to get we're going to get a stronger result. So this is the reason why the paired test is stronger. Now, how much stronger? Let's see if we can estimate how much stronger. So let's go back to page 13 here. Okay. I have a derivation here. I don't think it's useful to go through the derivation, so I won't do it. Basically, if I have a paired test, and I have n data in the paired test, that's equivalent to using the unpaired test with 2n, twice as many subjects. That's the result. Now, I'm not going to go through the derivation, but from the computation of the difference in the standard deviations from the paired and the unpaired, you can see that that's actually the case of what happens. So what this means is that for the same amount of data, it's as if it's paired, if they're legitimately paired, we have basically to do only half as many experiments if we have pairing in the data. Okay? And this is quantitatively what it works out to. Again, I'm trying to show you why this works out, which is because the variance is less in the paired case, and it's less because Fred is still Fred, whether, and he's not Mary, whether he's sober or drunk. Okay, what I'm going to do now is just kind of review where we are in all these statistical tests and what the formulas for them, are. Are there any questions about this, about the paired and the unpaired things? I found this very confusing initially as to why you would want to use pairs, and I thought it was worth going through this to show you what's going on in the paired test, which is that the variance is less, and so that increases the t-value and makes the deviations more statistically significant. Okay? Okay, so let's review all this together on the test to see where we are. So this is the summary of where we are today. Okay. If we can, in the first case, we do just an experiment. And what we're doing is comparing the result of that experiment to the real value which we know somehow. And as I said, sometimes this is actually the case. For example, let's say, for example, we flip a coin 30 times. We know that about 15 times it should be heads, for example. So we know what the correct result is. So in this case, this corresponds in terms of the z statistic. We have an experiment, and we have known. From the experiment, we're going to measure the mean of the experimental values and the number of the experimental values. We know the mean to be expected, and we know the variance to be expected. And from this, we compute the z statistic will be the difference between the mean of the experiment and what was suspected divided by the known standard deviation divided by the square root of the number of measurements. And from this z, we use Gaussian probability to get the p-value. Okay. And we never do this, usually, because this assumes that the number of values n is large. So instead of doing this, we use the t-test variant. In the t-test, we have the experiment and known. So in this case, only the mean is known. We have the mean from the experiment. We have the standard deviation from the experiment. And we have the number of values from the experiment. And from this, we can compute the degrees of freedom from the experiment. The degrees of freedom nu equals n minus 1. And we can compute t, the t statistic, which is the difference between the experimental mean and the known mean divided by s divided by n minus 1. So this, and we should use this because n is less than infinity. Okay, we're okay on this first case. Second case we discussed, so 2, is we do two things. So we've run two experiments. We have an experimental group, two things, we may have two data sets, data conditions. We have an experiment, and we have a control. And what we're trying to tell is, which I'll symbolize by X and by C, and we're going to test is the difference between the experiment in control due to chance. So how do we do that? Well, now we just have data measurements from the experiment. Let me just call this I've worked myself into a corner here. From either the experiment or the control. So we have nothing is known in some absolute sense. From the experiment, we have the mean of the experiment, the number of times we did the experiment, and the variance of the experiment. We know from the control, we have the mean of the control, number of times we did it, and the variance from that. And we can create the z statistic, which is, I said, something like the difference between the experiment control over the SEM combined from both of them. And I showed that that was equal to mx minus the mean of the control divided by something that looked like this. It is the variance of the experiment squared plus the variance of the control squared divided by the numbers of the control. And I said, again, we don't use this ever because, again, this assumes that n is going to be very large. So instead, it would probably be better to use the t business, which doesn't assume that n was large. So in the t business, again, we have experiment and control. From the experiment, again, we have the mean in the experiment, the number in the experiment, and the standard deviation from the experiment, which I'm going to write as S, because we're going to compute this from the data. We're not going to fake it in some way from what we think is the population. And we have the same things for the control. And then we form the t statistic, which is like the mean of the experiment minus the mean of the control divided by sigma experiment squared over n experiment plus sigma control squared over n of the experiment over the square root. And sigma, one way to this is just sigma, sorry. Where sigma itself is the combined sigma from both, which we've seen goes like nx times sx squared plus nc times sc squared divided by nx plus nc minus 2, where the number of degrees of freedom is nx plus nc minus 2. So then this is the statistic we would use with this number of degrees of freedom. And if I have made a mistake in this, it's in Spiegel's book. So I think this is correct. Okay, again, I've gone through this business of deriving a statistic that I don't want you to use to show you where it comes from, to give you a feeling for where this t comes from. Okay, that we're always comparing the differences of things with respect to SEMs. And this is what I said that I do when I read other people's data. I compute the combined SEM. I see the difference, how many times the difference between the two things are compared to that SEM, and which is this formula, and that tells me whether things are meaningful or not. Now, the difference between the Gaussian and the t-test is not huge, so this is actually a pretty good estimate of what's going on. Okay.
So, what some people do, like all the difference, let's say, between how many standard errors.
Right.
You have between the two, there's overlap.
Right.
It doesn't work all the time.
Well, it does work. What you have, the point of doing it this way is that this allows you to do the case where the two standard errors are different. If the two standard errors are the same, then you should multiply by the square root of 2 before counting the overlaps. But it's not so bad, because we're talking very rough estimates. Remember, we want to get roughly 2 SEMs. So if you multiply by the square root of 2, then you need about 1.5 SEMs. If you're going for 2 SEMs, then that's going to be statistically significant. So roughly 2 of them is going to be okay. Okay, so that was the second case that we did. And the third case was this paired case. In the paired case, we're looking at the, we have all the data from 2 groups, X and the control. And we have all of the data, but what we're looking at all the time is the differences between I don't like that. We have the control and the experimental where we have data, but what we're really interested in the differences between the experiment and control. So we have now the mean, which I'll say as D. We have the mean of these differences. We have the number of the differences. And we have the standard deviation of these differences. And now we can write that the t-statistic is equal to the mean of these differences divided by their standard deviation over the square root of n minus 1, and the number of degrees of freedom is n minus 1. There's another type of statistic which I'm going to describe more when we do analysis of variance. So I'm going to mention it now, but we're really going to do it later. And so far, just about all the questions we've been asking are, is this mean like that mean? That is the null hypothesis is that the control mean is equal to the experimental mean, or the difference is due to chance. We could ask a different question. We could ask, is this variance or standard deviation like that standard deviation? That is, we can do some experiment that produces a standard deviation, SA, another experiment that produces a standard deviation, SB, and we could ask, is the difference between SA and SB due to chance? And the way we do this, actually, we create a statistic called the F statistic, which is the ratio of these two, and then we can test the F statistic. And this is called an F test. And I don't know why it's called an F test. I don't know where the F comes from. I think it's actually named after Fisher. So this may have been done by Fisher, who did a lot of work on statistics or social sciences, or may have been named after him. So it's probably from Fisher. So I do know what it's named after. I'm not going to describe this in more detail. This is the basis of another sort of test called analysis of variance. And when I come to analysis of variance later in the term, I'll describe in more detail how the F statistic is used to do analysis of variance. That's all I really wanted to cover today. That's really quite a lot. And I think the crucial take-home lessons of what we had today are, you can look up in Spiegel's book how to do these tests for any specific data set. And so if you need to do these tests, you can see how to do it. What I've been trying to do today is to motivate where the formulas come from, to really emphasize that what we're dealing in the derivatives of these tests are the standard errors of the mean, and in terms of the numerators of the test, the difference between the means. In that, in the standard Z statistic, we're dealing with a Gaussian distribution. And when we go to a t-test, we're dealing with a somewhat modified distribution to handle the fact that we don't have all the data we would have from an infinite sample. And I think it's useful to do this because otherwise, if you just look at these up in the book, you have no idea where any of these formulas come from. And what I've been trying to do is to give some motivation as to where the formulas come from, and to give you a sense that they're really very reasonable, that they're really saying we look at the differences normalized by how much we think the spread should be. And the correct measure of that spread is the standard error of the mean. And then they're adjusted for the fact that we don't have infinite data, or they're adjusted for the fact that we have pairwise comparisons and we can look at things in a different way. And I think, to me, this is a better approach than doing the complete formal derivations of the test, which would also use the same principles, because that's how you derive them. I think, although I've read but have forgotten the derivations of these that I've seen. So, but I don't want to do that. I don't think that would be so useful. But I want to give, in this hand-waving sense, where they come from, so you have a feeling for what's going on here. Do you have any questions on this? I think if things have been unclear, these are all covered pretty well in Spiegel's book, which they also have the first edition of in my friend's lab in Israel. So I felt good it wasn't your second edition, because we agreed that funny white combination of colors. So you have examples on homework number 3, if there's anyone who hasn't gotten homework number 3, on doing these statistical tests, as well as doing the chi-square test. So you can go back now to see whether the Gaussian that you fit is any good or not. And if for some reason you need any of the numbers that you computed before, you should speak to me and I can negotiate lending you back your homework on the first set. Otherwise, I think we might as well stop here because I think that's really enough for one set. Okay.